These notes are going to go back over some of the things that you learned with the two Pogles that you did. I'm going to, you can read this. I'm not going to read it to you on the video, but let's just look at some key things to maybe highlight on there in here. Okay, so first off, this, where it says this part, the charge felt by the electrons, is called the effective nuclear charge. And here in the Pogles, we were mostly referring to force, attractive force. And so that's kind of what in this set of notes, when they talk about charge or effective nuclear charge, that's what they're talking about. And so effective nuclear charge, like nuclear charge is just based on the number of protons in the nucleus, but effective nuclear charge, that's taking into account not only how many protons are in the nucleus, but also the distance of the electron from the nucleus. So it's kind of a combined effect of those two things. All right, and so here, let's see. All right, let's just keep going with this. Okay, so again, here they're just showing sort of a visual of the effect of, in this case here, we're looking at where we are going. So let's see, from here, this one to that one, we're like increasing the number of electrons. And remember in the Pogle, we said that the force experienced by each of the electrons was going to be very close to the same. And we modeled it the same in the Pogle. This is getting a little more specific because if you remember, it did talk about that there is a little bit of a repulsive effect from the presence of other electrons. And so that's just what this is showing, is that we do, if we add another electron, we do have a little bit of a change in that force. It reduces it slightly, and that's just the repulsive effect from the other electrons. All right, and then here, this is showing the definite effect of if we increase the protons, we increase the charge, or the force felt by each of those electrons, the attractive force on there, which is kind of, again, consistent with what we learned in the Pogles. Okay, so in the Pogles, we talked about ionization energy, and it's the energy required to remove an electron from a gaseous atom in its ground state. All right, and we're not going to worry about the whole gaseous atom part, just the amount of energy required to remove an electron. And so the things that we want to see is that in looking at it, we'll use I for ionization energy, and then I1, that is the energy to remove the outermost electron. So, and this equation is showing that we put the energy in, so energy on the left side of the equation, that's energy going in. And so with our neutral atom, and it loses an electron, so we get an electron produced, and then the ion formed has a +1 charge because it's lost an electron. Okay, but then we can keep going. So you'll also see where we have like I2 and I3. So I2 starts with the positively charged, the +1 ion, right? It loses another electron, and now it's a +2, and so forth. The I3 would be to remove the third electron. So it's starting out as a +2, and then we lose an electron, and it forms the +3. Okay, so that's when you have I with different subscripts, that's what that refers to. Okay, and so here we talked about the summary of the trends. So going down a group, they become easier to remove because they are at an increasing distance from the nucleus. And remember before we said, if I'm looking at any trend as I'm comparing things going down a group, the explanation for that trend is because every time I go down one, I have another whole energy level of electrons, which means it's that outermost electron is getting further and further from the nucleus. And that's what is the dominant explanation for the change in the ionization energy as I go down a group, or the change in any of these trends as you go down a group has to do with the outer electron is further from the nucleus. And then here, likewise, going across a period, ionization energies increase. And the key thing there, the nuclear charge is increasing. So as I go across a period, right, my electrons are in the same energy level. So we're not getting a huge increase in distance, but I'm adding a proton. Every time I move one element over, it's got another proton in its nucleus. And so for any of the trends as I go across a period, the explanation has to do with that increasing number of protons, increasing nuclear charge. Okay. All right. So now, when we looked at ionization energy, we didn't go into detail as to why I talked about it a little bit, but we noticed that ionization energy is not a pure trend the way that atomic radius is. It's got a couple of places where instead of, like as I go across a period, instead of continually increasing, it like drops down and then goes back up. And so there are two places this occurs, and we're going to take a look at those and look at the why. Okay, so here, right, all right, so let's look at here as I go. Remember we said as I go from the S block to the P block, right, that P block is slightly farther from the nucleus, which is why it's going to be a little easier to remove. And so as you can see, if I'm taking the outer electron from beryllium, it's oh, that didn't work. Let me get a smaller highlighter. That's way too big. I don't know if that's a highlighter or a marker, but we'll go with it. All right, it's going from the 2s. Oh, that's gonna, sorry about me. Will this let me change the size? Maybe I can. Can I? There we go. I think I got a small highlighter now. Yeah. All right. So from beryllium, the outer electron is coming out of that 2s, which is closer to the nucleus than boron's outer electron is in a 2p. Okay. So slightly easier to get that 2p electron than it is to get the 2s electron. So that's where at that point in the going across the row that we see where it drops down and then it starts going back up again. All right, so that's the explanation for that one. Then here, if we continue across, right, so this is the one here that we just talked about, that blip right there. Now, the other place we get a blip is halfway through the P, and going from having 3p electrons to having 4. And so if you remember back to our electrons unit, all right, what's the significance of that? Well, let's go down here. All right, and let's look at what our diagrams would look at. So for nitrogen, right, if I do my orbital diagram like that, right, here, do it for oxygen. Goes like that, and then, right, it doubles up. And so what happens is that it is slightly easier to remove an electron from an orbital that already has an electron in it that's paired than it is to remove an electron from an orbital where it doesn't have a matching one in there. So kind of think of it like you've got that little bit of repulsive effect. So if we go back to our boarding house thing, it's sort of like you've got somebody there that's helping you by pushing the other person out of the bed, out of the orbital, okay? All right, and so then once that happens, then it starts to go up again. Because as we get further out, right, we would still be, for the other ones, they're just going to be paired in with these two P's on there. Okay, all right. So now let's take a look at the kinds of questions that you might see, and you're going to do a quest, and so these are going to be the kind of questions that you see in the quest. So we want the orbital in which an electron would experience the highest attractive force, Z effective, and which would mean it gets the highest ionization energy. Okay, if we look at these, if we're comparing these are all going across a period. Like those are all in the same, they're all in the third period. And so there, normally the one farthest to the right would be the highest. However, right, this one, phosphorus, has 3 electrons in its outer shell, right? Whereas sulfur, whoops, what am I doing? Whereas sulfur, right, has that. So for in this case, phosphorus would have a slightly higher ionization energy. Okay, number 2, match the following electron configurations with the appropriate ionization energies. All right. So first off, let's figure out what these elements are. So if I look, this one ends at 5s1. So this is strontium. This one ends at 4s2. So this one is calcium. And this one ends at 4p6. That is krypton. Okay, so these are, okay, so if we look at where they're located, okay, all right, now that I got a periodic table I can refer to. All right, so strontium, calcium, krypton. So let's just look at those. All right, so strontium, calcium, krypton. Okay, so if we're looking at those, which one would be the highest? Well, okay, definitely, so calcium and krypton are going to be higher because they are closer to the nucleus, their outer electron, because it's in the 4th energy level, whereas strontium is in the 5th energy level. And then between calcium and krypton, krypton has 36 protons, right? 36 protons versus calcium only has 20. So that's going to be the highest. And then this one, because the electrons are further away, that's going to be the lowest on there. So let's go back. So the highest is the krypton. So krypton is that one. And we said the lowest was strontium. So strontium there. And then calcium is going to be the one in the middle. All right, then it says, which of the following? So I have sodium, potassium, lithium, cesium. So if we look at those, let's get my giant eraser. All right. So those are all here, right? And so here, these, the outer electrons are in the 1, 2, 3, 4, 5, 6, 6th energy level. That is in the 2nd. So that's why, right, going down a row, it gets less. So here, if we go back to the worksheet, the largest ionization energy is the one where the electrons are closer to the nucleus. So that would be lithium. All right. So here, these are sequential elements in period 3, and they want us to assign elements based on the trends above. So here, what we're looking at, right here, that's one of those break points, right? It goes down and then it starts back up. And there's another one. So this here to here, that means that's in the middle of the P block. So if we go back, look at our periodic table, and it said it was in n equals 3. So the break in n equals 3 would be, the third period is going to be there. So sulfur, it's sulfur, phosphorus. So sulfur, phosphorus, silicon, aluminum, and then we get that other jump and going aluminum back to magnesium is where that one would be. Okay. So here, now, another type of question that you'll see is where they give you a series of ionization energies. And whenever you have like an I1, I2, I3, those are removing electrons from the same atom, all right? And one thing to notice about this is it always increases. I2 is always greater than I1. I3 is always greater than I2. But the other thing that we're going to notice is that the amount that it increases is not always like the same proportion. And what you'll see with these is that you'll go along and there'll be one increase that is always much, much larger than the others. So in lithium, right, lithium that occurs when we're, and let me not mark it that way. I'm going to just put a vertical line, would be better. All right, so in lithium, let's change colors now. It's right here, right, going from 520 to 7,300. That's the big jump. And we'll see in beryllium, it's going from I2 to I3. That's our big jump. In boron, right there, there's a bigger increase. And then carbon, it occurs in trying to get. So what this is saying, in lithium, it's much, much harder to get that second electron than it was to get the first. In beryllium, it's much, much harder to get the third electron than it was to get the second. So let's look and see what's happening. What's the explanation for that? All right, so we're going to be jumping back and forth here a little bit, but let me, again, erase. All right. Okay, so lithium, let's look. Lithium, all right, so I1 in lithium is taking this electron here, right? I2 is taking this electron here. So what just happened? Well, I1, the electron is, for lithium, I1 is a 2s electron, and I2 is what? It's a 1s electron. So we all of a sudden are trying to take an electron now that's from an energy level that's closer to the nucleus. Okay? And these, it's all coming from the same element, so the protons are always going to be the same. But that distance from the nucleus all of a sudden takes a big jump. And what we'll see is that once we've removed the valence electrons, then that's where we're going to see that big jump. Okay, so the explanation for the big jump is that all of a sudden, you know, I'm going along. So let's look at, say, for beryllium again. All right, so for beryllium, right, here's I1 is this one, I2, and then there I3. We're all of a sudden taking in trying to take an electron from an energy level closer to the nucleus. So that's why we get that big jump. The other cool thing about it is that all of the electrons that were taken before I'm trying to take the one from the inner level, those are valence electrons. So I can also use it to determine how many valence electrons are present in the element on there. So again, and we'll see and it'll play more of a role when we get into our bonding unit. But to look, the valence electrons are the s and p electrons on the same, on that outermost energy level. So I can go to the row the element's in, right, because that represents the highest energy level that it's got electrons in, and I can count the s's and the p's. So say I want to do aluminum. So aluminum has 1, 2, 3 valence electrons. So that means that for aluminum, I would go, I1 would be a certain value, I2 would be higher, I3 would be higher, but then I4 is going to take a bigger jump because now I'm trying to take an electron from an energy level closer to the nucleus. Okay, so let's go back to our sheet here then. All right, so these are ionization energies for 3 elements in the third period, and we want to label, it says to label each box. So they're in the third period. So let's look and see. So here, the big jump is right there. So I take 1 electron, and then all of a sudden I'm trying to pull from the next, a closer energy level. So N equals 3, sodium is the one that has 1 electron in the third energy level, and then all of a sudden now I'm trying to take electrons from the second. All right, likewise here, right, see here it doubles from I1 to I2, but then here, there's our big jump. So that means that these 2 electrons are in the third energy level, but then now it's trying to take one from the second. So magnesium, I take 2 electrons, and then now I'm trying to pull from a closer energy level. And then here, the next one right there is my, where I get that big jump. So that means these 3 were easier to take, and then all of a sudden I'm trying to pull from the second energy level. And so that would, which we just talked about a minute ago, that's going to be aluminum. All right, so we have two elements here, and I'm going to write these out because I don't like looking at them. So X is 170, 350, 1800, and 2500. And then Y is 200, 400, 3500, and 5000. All right, so first off, let's see, where is our big jump? So it doubled there, but then here, this one, it went, there's my big jump there. And then the same thing here. So I2, there's I1, I2, I3. So I2 to I3, there's our big jump. So this, right, there are our valence electrons. So both of them have 2 valence electrons, which means, right, they're alkaline earth metals. So they're both in group 2. And then what else do we know? So looking at it, they're both in the same group. The next question is, which one is higher up in the group? Well, higher up, electrons are closer to the nucleus, so we're looking for the higher one. So that means that Y is above X. Okay, so it could be, so X and Y. So that means that if X is sodium, Y would be lithium. Or if X was potassium, Y could be sodium. So that's why they say multiple possible answers for that. Which of the following has the largest I2? Okay, so a large I2, that would mean that it has 1 valence, right? Because if the jump comes in going from I1 to I2, that means the first electron was easy, the second one took more energy. And so in looking at these elements, right, let me flip back to our periodic table. Potassium is the only one in that row, right? Because there's iron, what were they? Iron, calcium, scandium, right? So potassium is the only one that has one valence electron. So I take my first one, and then it's going after one that's on the third energy level. Okay, so that would be this guy here. All right, so now we're looking at which pair has the higher ionization energy. Okay, so here's the thing. In looking at these, the first thing we do is compare the number of electrons in a question like this. And then, if it has more electrons, it's going to be easier to take one than if it has fewer. Okay, so here, number of electrons, magnesium has 12. 2 electrons. Magnesium plus 2 has 10. All right, and the other thing is that magnesium plus 2, right, magnesium, it's taking a 3s electron, whereas if I already have lost 2, then this would be trying to take a 2p electron that's closer to the nucleus. So the higher ionization energy would be that one. Okay, whereas here, how many electrons do I have? Oxygen has 8. Oxygen with a -2 charge has 10. Okay, it's going to be harder to take. So more electrons means it's going to be easier to take the electron out. Okay, so now then the question, so that's comparing atoms and ions of the same element. So what do we do if it's not? And I wrote over that charge. There we go. So let's look at, all right, where I'm comparing here. So first thing, I always look at the electrons. So K with a +1 charge has 18. And chlorine with a -1 charge has 18. All right, what do we do now? Okay, first off, I don't remember if we've used this term or not. Isoelectronic. Iso meaning same. Electronic meaning same number of electrons. So then what do? Same number of electrons. All right, well, then what's the other thing that would affect it? The protons. So potassium has 19. Chlorine has 17. Okay, so more protons, higher ionization energy. Okay, so potassium +1 would have the higher one. All right, let's look at this one. Electrons, phosphorus with 3 negative is 18. Sulfur with 2 negative is 18. So again, we're going to look at the protons. Phosphorus has 15. Sulfur has 16. So again, more protons, higher ionization energy.